These notes are properties of rational functions, part 2, and then I will call them day 2. We were talking yesterday about a bottom-heavy rational function has a horizontal asymptote, and a top-heavy rational function has a oblique asymptote. And then if we have the same degree on the top and the bottom, then we end up with another horizontal asymptote at y equals a divided by b, whatever that may be. And we'll look at some of those examples here today. So going to take a little bit different perspective here on problem number 2. And let's start by graphing in our calculator. I'm not going to graph it on the screen yet, but let's look at it on the calculator. So if we go ahead and we type this into the calculator, we're going to go to y equals, and our alpha y equals. And then we're going to type in 9 divided by x squared minus 9. We can look at the picture. Like I said, I'm not going to graph it just yet. But there's our picture. So we have some idea, at least, of what the function's going to look like. And for you, you've got the calculator that you can, unbelievable, keep at your desk there. But for me, I like to start by looking at the domain. And I know that we didn't ask for the domain on this one, but the domain is determined by taking the denominator, the bottom of the fraction, and setting it not equal to 0. And if we factor this, we get x minus 3 and x plus 3. And that means that x minus 3 doesn't equal 0. And x plus 3 doesn't equal 0. And I hope that you don't have to do this work, but we end up with our domain being x doesn't equal 3, and x doesn't equal negative 3. And if you prefer, you can write for your vertical asymptotes. Abby? Yeah. So we get x equals 3, x equals negative 3, and if you prefer, you can write x equals plus or minus 3. Because it is going to be equal. And if we look over here on our graph, then we could put that in right now. X equals 3, x equals negative 3. If we look at the function a little bit more closely, what we have now with the denominator factored is we have 9, and then we have the x minus 3 and the x plus 3 in the denominator. We're not going to cancel anything out. And because we don't cancel anything out, then we don't have any removable discontinuity. If you prefer, D and E. So the question then becomes, do we have a horizontal and, not and or an oblique asymptote? And that's when we go back and we look at our numerator degree. Well, in the numerator, our highest degree term is 9, which is degree 0. We don't have a variable on it. Our denominator degree, our highest degree term is x squared, so we do have a degree there of 2. And what we can then tell from that is that we have a bottom-heavy function. And if we look back at our chart, bottom-heavy says that we have an asymptote, a horizontal asymptote, at y equals 0. We don't even have to calculate anything. And the thing is, if we have a horizontal, we don't have an oblique, and vice versa. So no oblique here. I'm going to erase my degrees so that we can go ahead and graph this function. But when we put in our horizontal asymptote, in this case it's the x-axis. And now let's go back and look at our picture. So the one thing that I noticed right away is that it looks like I have a y-intercept at 0, 1. And as we scroll through here, sure enough, 0, 1. So we've got a part of our function here. And then if we look at the picture one more time, here I'm not sure if we can get too many good points, but let's see if we can find something after 3 or negative 3. A decent point to graph. 4, 5, 6, 1/3. We don't really have anything that's going to work for us in terms of being able to find on our calculator. So we've seen the picture and we know that it looks roughly like that. It's a sketch. It's a little bit more accurate than some, and not as accurate as others. But luckily on that one, we didn't have an oblique asymptote because that's the one that's causing us the most trouble. But we know that it's going to show up again somewhere. Yes. So if we look at example 3, again, maybe what's going to be easiest for us is if we graph it first. I'm not going to draw the picture first, but it gives us some idea of what we're looking at. So if we do alpha y equals for our fraction here, and then we've got x cubed minus 2x squared minus 3x, and then we're going to divide by x squared minus 4. And again, we're going to draw this picture in a few minutes. So, but at least this gives us some idea of what we're working with. So what we are going to eventually have to end up having to do is we're going to have to factor the numerator and we're going to have to factor the denominator because we want to find our vertical asymptotes. I usually start by factoring the denominator, but it's not going to make that much difference because we need to do both. So if we factor our numerator here, the first thing to notice is that we've got a greatest common factor of x. And if we take that out, we're left with x squared minus 2x minus 3. So we need to factor a little bit more. And the factors of 3 are 3 and 1. It's going to be minus 3 and plus 1. And our denominator is the difference between two squares again. And we have x minus 2 and x plus 2. So the thing about this is, the first thing that I notice is that we cannot cancel anything. And if we cannot cancel something, there's no removable discontinuity. But before I do anything else, we didn't cancel anything, no removable discontinuity. Our vertical asymptotes, they do come from the denominator. And what we've got is we've got x minus 2. We can set that equal to 0. X plus 2, we can set that equal to 0. And ultimately what we end up with is we end up with x equals 2. And over here, we also end up with x equals negative 2. If you prefer, write x equals plus or minus 2. So we've got a couple of vertical asymptotes, so let's go ahead and get that part graphed right now. while we're thinking about it. And negative 2. And then what we're going to have to do is we're going to have to go back and look here and see our degrees. We want to determine whether we have a horizontal or we have an oblique. And in the numerator, our highest degree term is x cubed. So that means degree 3. Our denominator, our highest degree term is x squared, which means degree 2. So what we've got then is we've got, it looks like 3 is bigger than 2, so we have a top heavy. And top heavy, if we look back at our chart on our front page of our notes, means that we have an oblique. So no horizontal on this one. We have an oblique. So we're going to have to use synthetic division. And when we set the synthetic division problem up, I'm going to write the numerator in its original form, which is x cubed minus 2x squared times 3x. And then we're going to divide by, I'm going to write the factored form of the denominator, which is the x minus 2 and the x plus 2. The reason is synthetic is very limited. We cannot use synthetic division with x squared. But if we write it in its factored form, then we have an x to the first, and we can use that. We want to come up with our oblique asymptote, which is going to be in the format of y equals mx plus b. So when we do our synthetic division, the first thing that we're going to do is we'll write our upside down division bar. The number in front of the x cubed is a 1. The number in front of the x squared is 2, and it's actually subtracting 2. And then we have minus 3, the number in front of the x. Over here, if we divide by x minus 2, we need to change the sign. So our first division is going to be with the 2. And we carry this first term down, so it's 1. 2 times 1 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0, and negative 3 plus 0 is negative 3. When we started with an x cubed polynomial right here. We divided by a first degree, which means that when we finished here, we now have an x squared polynomial. But what we did is we only divided with this factor. We actually can divide again. We did x minus 2. Now we're going to deal with the factor of x plus 2. But remember, it's plus 2, so in order to divide, we're going to divide by a negative out here. And we're going to carry down our 1. And we end up with negative 2 times 1 is negative 2. 0 minus 2 is negative 2. Negative 2 times negative 2 is positive 4. And negative 3 plus 4 is 1. But we started with an x squared term. And now what's going to happen is we're going to end with x. Each time we divide, our degree becomes 1 less, x cubed. Then our degree became x squared, 1 less degree. When we divide it again, it became x to the first. So when we put our variables back into this, we're left with 1x minus 2. And this last part here, this remainder, is really 1 over x squared minus 4. But there is a long-winded explanation for this. But really, when it comes to oblique asymptotes, what we want to deal with is we want to deal with this part of the function. We don't need any information from the remainder. We can ignore that remainder. So our oblique asymptote is y equals 1x minus 2. We can put this back into our graph as well. Remember that our slope then is 1 over 1, the number in front of the x. Our y-intercept is negative 2. So when we come over here to graph, b equals negative 2. And then our slope is up 1 over 1, up 1 over 1, up 1 over 1. Or we can go down 1 to the left 1, down 1 to the left, down 1 to the left. Starts at negative 2. And so what we have is, here's our oblique. And the nice part about obliques is you can check them on your calculator. Type that in. Y equals x minus 2. Does it make sense? It does when you look at the picture. We can check it, so to speak, there. So we've got that now in our picture. And what we really want to come up with, and I'm going to take out the oblique for now, just because we're going to look at the table, because we can finish by looking at the table and coming up with some values on here. I'm going to scoop back here. And we know what the picture looks like as well. So I'm not going to be super accurate, but, oh, there it goes again. There's our picture. But when we look at the table, we can get some values. We've got negative 1, 0 and 0, 0. So when we look at our picture, we're in here. So negative 1, 0 and 0, 0. Oh, our graph is somewhere in there. Not super fancy. A rough sketch. When we continue to look at our table in our calculator, we also see a point like 3, 0. Let's see if we have any other nice ones that we can work with here. We have 3, 0 and we have 8, 6. So 3, 0. 1, 2, 3, 0. 8, 6. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. It should be underneath there. It's really here, but if you look back at the picture, it looks like that. And we can go back one last time and look kind of to the, not even kind of, to the left of our vertical asymptote at x equals negative 2. So if we go back here, see if we can find negative 4, negative 7. I thought we had one more, but it doesn't look like it. But negative 4, negative 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Again, the picture off a little bit, but when we go back and look at our graph, in terms of the picture, we've got this value like that. So one last one. It's nice here on example number 4 that we have the numerator already factored for us. So we need to factor the denominator, and before we even start, let's type it in our calculator and look at the picture. I think that'll be a little bit helpful. So we have 4 times x plus 1 times x minus 3. Gotta hit the 3. And then we've got our x squared minus 1. And we are going to have to factor that, but we can still look at the picture without doing that. And there's a picture. So it gives us some idea here of what we're working with. So that when we find our different asymptotes, the question is, do they make sense? Compared to our picture on our calculator, and then when we draw a sketch of them, do they make sense? So like I said, we need to look at this denominator when it's factored. In x squared minus 1, x and x, 1 and 1, difference between two squares, different signs. And what we see on this problem here is that we have something exactly the same in the top and in the bottom of our function. We have an x plus 1. So when we cancel that out, that means that we're not going to have a vertical asymptote at that value. To find that vertical asymptote, we simply take the one that's still remaining and set it equal to 0. We can add 1 to both sides. We get x equals 1. But the removable discontinuity comes from the value that we canceled out. We canceled out the x plus 1. And if we set that equal to 0 and subtract 1 from both sides, we get x equals negative 1. That's going to be our x value of our removable discontinuity. And I should have drawn in my asymptote, but I'll draw that in a minute. But to find the other part of our ordered pair here, what's still remaining in the problem is 4 times x minus 3. The parts that didn't cancel out. 4 times x minus 3 divided by x minus 1. And we're going to take this value of negative 1 now. We're going to put that negative 1 back in for this x. But we're also going to put it back in for this x to figure out that other value. So it's going to be 4 times negative 1 minus 3 divided by negative 1 minus 1. And if we simplify that, we get 4 times negative 4 divided by negative 2. And 4 times negative 4 is negative 16 divided by negative 2. And negative 16 divided by negative 2 is 8. So let's put in a couple things here before we determine whether we have horizontal or an oblique asymptote. Let's draw in our vertical asymptote, which is going to be x equals 1. And the other thing that we're going to put in here is the removable discontinuity. Negative 1, 8, 1, 2, 3, 4, 5, 6, 7, 8 will have an open circle at that point. -1/8 is going to be an open circle. Instead of normal filled in circle, it's going to be open. It's not included. But now what we can look at is we can look at what still remains. We're left with 4 times x minus 3 over x minus 1. If you prefer, that's 4x minus 12 over x minus 1. We want to decide whether we have a horizontal or an oblique. So in our numerator, should have written in a different color, but in our numerator, we have 4x. And our degree of that is 1. In the denominator, we have x. The degree of that is 1. And because we have the same degree on the top and on the bottom, that means we're not going to have an oblique. We're going to have a horizontal. And our horizontal is going to be at y equals the number in front of the x on top is 4. The number in front of the x in the bottom is 1. It's going to be at y equals 4. And we can draw that in here before we finish by drawing in the complete graph. So there's our horizontal. If you go back and look at the picture on your calculator, that should make sense. If we look here, does that seem reasonable? It seems reasonable. So then we can come over here and we can find some points maybe that we can use to help us graph. Like 2, -4, and 3, 0. 2, -4, and 3, 0. We've got a branch like that. And then when we go again and look at another set of particular ones, we've got the -3, 6. I think there's one more. -3, 6 and -7, 5. -3. 1, 2, 3, 4, 5, 6. And then what did I say the other one was? -7, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 9 and 3? Yeah. Oh, yeah, positive 9 and 3. But I'm good here. So as we finish here, notice that I can't get it drawn in there, but we do have that open circle there where we'd have to lift our pencil to draw. And there's our picture.